Hello and welcome to section 2.6 and 3.6 on the derivative of the trigonometric functions. In this section, we introduce the derivatives of the 6 trigonometric functions and merge these forms with the rules introduced in sections 3.2, 3.3, and 3.7.
To begin with, what is the derivative of the sine function? We take the limit as h approaches 0 of the difference quotient for sine on the interval x to x plus h. This is a difficult limit that cannot be solved through techniques that we've previously learned. To proceed, we will need the sum formula for sine. Now, we have something to simplify. Break the function into two: cosine x sine h in the numerator of the first, and sine x cosine h minus sine x in the numerator of the second. It may appear odd, but the variable x can be viewed as a constant inside the limit, as the limit is only concerned with moving h values closer to 0. So we can rewrite the derivative of the sine function as cosine x times one limit minus sine x times another limit. The only way to differentiate sine is to determine these limits, and we need some series trigonometry and the squeeze theorem to do that. Let's put the derivative of sine on hold and calculate the limit of sine h over h as h approaches 0. We will find three functions which bound each other and use the squeeze theorem, the middle function being sine theta over theta, the function whose limit we are interested in. We will obtain these functions with the unit circle. This shouldn't be a surprise, as we are investigating trigonometric functions. Choose an angle theta between 0 and pi halves to cut a sector from the circle. Extend the radius until it intersects the line x equals 1. We make these choices to obtain three shapes with increasing area: a purple triangle, a blue sector, and a red triangle. The purple triangle lies inside the blue sector, which lies inside the red triangle. The area of each shape will give us the functions needed for the squeeze theorem. Let's begin by finding the area of the red triangle. This triangle is a right triangle with an angle theta whose adjacent side is the radius of the circle, so its length is 1. The area of a triangle is 1/2 base times height. We know that the base length is 1, but we haven't calculated the height. The height is opposite the angle theta, so we can use the tangent function. Recall the mnemonic device, SOHCAHTOA. Tangent is opposite over adjacent. As the adjacent side length is 1, the height length is tangent theta. Therefore, the area of the red triangle is 1/2 tangent theta. We move to the area of the blue sector. Recall that the area of the sector of a circle is 1/2 times the circle's radius times the angle of the sector. The radius of the circle is 1, therefore the area of the blue sector is 1/2 times theta. Finally, the area of the purple triangle. The area of a triangle is still 1/2 base times height. The base of this triangle is 1, and once again, we need trigonometry to calculate the height. We have a right triangle lying inside the purple triangle, with hypotenuse 1, angle theta, and the opposite length is the height. We use the sine function, as sine equals the opposite length, the height, divided by the hypotenuse length, which is 1. The height is sine theta, and the area of the purple triangle is 1/2 sine theta. From the unit circle, we have found three shapes with increasing area, and from these areas, we obtain two inequalities. With the first inequality, we can multiply by 2 and then divide by theta to obtain sine theta over theta is less than or equal to 1. We could divide by theta because theta was chosen to be non-zero, and we don't worry about the inequality changing direction as theta is positive. With the second inequality, we again multiply by 2. Recall that theta is sine over cosine. Dividing by theta and multiplying by cosine on both sides gives the inequality cosine theta is less than or equal to sine theta over theta. Again, we don't worry about the inequality changing direction because theta is positive and cosine is in the first quadrant, therefore it's positive. We combine these inequalities to obtain the desired squeeze theorem setup. We are trying to calculate the limit as theta approaches 0 of sine theta over theta. If you're particularly sharp today, then you've noticed that theta was chosen to be positive, but we want to take the limit from both sides as theta approaches 0. Technically, we can only use these inequalities to find the right-hand limit as theta approaches 0. However, you can rest assured knowing that the left-hand limit equals the right-hand limit we are about to calculate. Since cosine is continuous everywhere, the limit as theta approaches 0 equals cosine of 0, which is 1. As theta approaches 0, the constant function 1 approaches 1. Therefore, the left function and the right function both approach 1 as theta approaches 0. And the limit of sine theta over theta as theta approaches 0 is 1 by the squeeze theorem. Wow, that was an intense diversion from derivatives. Where were we? That's right. We almost had the derivative of sine. We only had to calculate two limits. The first limit we've just calculated as 1, and to save time, I'll tell you that the second limit is 0. Therefore, the derivative of sine is cosine. The remaining 5 derivatives are much easier to find now that we've calculated the derivative of sine x, and in class, they will be derived. The limits of sine x over x and cosine x minus 1 over x, as x approaches 0, are important and should be taken note of. You've seen the basics, now work towards mastery through practice and study.